Okay, so before we get to conservation of energy, I want to do a quick refresher on the Reynolds transport theorem. So step one to any problem we do with Reynolds transport theorem is draw a CV and add coordinate system. And there's some things that are actually important about this, right? That matter. Things you have to keep in mind. A, does your CV contain everything you are interested in? And that basically means, does your CV contain all the forces that matter, all the fluids that matter, right? If you have a tank on a cart and water's accumulated in there, you better include the whole tank, right? If you have friction on that cart or on some object, you better include enough of your CV so that you include that force. B, does your CV cut through any liquids or solids? So when it cuts through liquids or solids, we have to include any forces or we have to include any stresses that are in that liquid or solid. So stresses like pressures, right? If we know the pressures always act inward, two, or double I. Do you know stresses / forces in solids that you're cutting through? So if you're cutting through a pipe, for example, sometimes that results in a force. But not always, right? You have to look at the whole problem holistically. For example, in your homework, there was where we split a pipe in two and we're asking for you the force necessary to hold that pipe in place. That force is exerted by the pipe that you cut through, right? So it depends on how we ask the problem about whether or not you include those forces or not. And three, when you're cutting through fluids, do you know velocity do you know velocity profiles? This is really important. If you have to integrate, for example, if you have to integrate, then that makes the problem more complicated. If it's a uniform velocity profile, it means you can get rid of integrals. So, do you know velocity profiles? And lastly, we want to know see where you pin XYZ, right? So your coordinate system, where do you put it? And questions you ask yourself for this is, can you make v xyz equal to 0 in CV? If you can, it might be worth it to pin your coordinate system such that that's true, because that gets rid of the triple integral, right? And basically, try to think, how can you make problems easier? And pinning the your coordinate system will never really reduce the number of unknowns you have, but what it will do is it will make the math easier. So you don't have to do the triple integral, for example. Well, you never have to do the triple integral, but you might be able to just get rid of that whole component of that equation and then only have to deal with stuff that's entering and leaving your control line, for example. 2, then you choose an equation that helps you. Choose an equation that helps you. So, for example, conservation of mass. It relates flow rates, velocities, and mass accumulation or volume changes. It relates all those things together. So if you ever have, like, for example, a couple, like 2 unknown velocities, but you know a couple cross-sectional areas, you want to use conservation of mass to reduce the number of unknown velocities, that's perfect, right? That's perfect for conservation of mass. Or if you know mass accumulation and need flow rates, things like that, because you know the density. You have to, this is all a game of understanding what unknowns and you have and what constraints you have in order to solve for those unknowns. B, conservation of linear momentum relates forces to velocities and flow rates. And C, conservation of energy relates heat and work to velocities, pressures, and temperatures, and heights. Great, so we've chosen an equation that helps limit the amount of unknowns that we have. We might have to apply the steps 2, 3, and 4 multiple times if we have more than one unknown, right? And then we apply assumptions to simplify problem, right? So A, the easiest, steady state, basically means d dt of whatever is equal to 0. Now remember, if you're accumulating mass, you can't assume steady state. If your control volume is changing size with time, changing volume with time, you can't assume steady state. So we don't always get to assume steady state, but when we do, it's wonderful. B, uniform flow plus density is equal to a constant results in surface integrals going away. So when we integrate over the control surface, it stops being a control surface integral and suddenly becomes a summation of the density times either 1 or 2 velocities times our area. C, good choice of CV can make the dot product, so W dot N hat, very easy. In other words, plus or minus W. And don't be afraid to, how do I put this? Rename integrals that, or quantities maybe, are obvious, i.e. m dot cv is equal to d dt, the integral of rho dv, right? That is just equal to m dot cv, and sometimes that's what we're asking for. So you don't have to do the integral, you just solve for. its value. Step 4, solve. A, integrate if you have to. B, count unknowns. Count unknowns and repeat 1 through 4 if you have to. And remember, don't forget Bernoulli's. Bernoulli's is a tool you can use as well in these problems to help add constraints. You have to assume inviscid flow then, but that's okay. A lot of times we will tell you if that's an appropriate assumption. So our next video, we're going to introduce conservation energy into this whole Reynolds transport theorem and show several different ways in which that equation can simplify and is useful for different applications.